It is Monday. September 14th, 2020. This is Physics 174. It's 11 a.m. Page 1. Yes. Trash. Coming up, future attractions for this class. Homework 5 is going to come out hopefully this afternoon. Quiz 5, hopefully will be there, but you won't be able to see it until Wednesday morning, the usual time. Fingers crossed. Exam number 1 is also coming up. It's going to be next week, around Wednesday of next week. I think that's September 23rd. That's not the important thing. The important thing is the day of the week. Wednesday at the earliest, Friday at the latest. So definitely not next Monday, but definitely sometime Wednesday or Friday of next week. What's the coverage? So I can start studying now. If you got a little extra time, start studying now. You want to strike early on these exams. Usually exam 1's most people it's usually the highest average. Doesn't mean there's people who don't have problems with it. So just try to, if you think you're having problems, try to get going on it now. Do a few of these practice problems or come see me for help. So the coverage is up to and including projectile motion. And this will be from chapter 4, covered on Wednesday. So next time we meet, we'll cover the what's left for this first chapter, our first exam. And then we'll work through examples for the remainder of the week. And then we'll have like a little review or something like that on Monday. We might move a little bit ahead of how time permits for the new material for the test number 2 with radial motion. We will not finish all of chapter 4. Radial motion, I believe, is the end of chapter 4, so that will not be on this exam. And of course, today what we're going to do is we're going to start chapter 4. Got a little video I can show you.
Receivers out to the right. Flutie flushed. Throws it down. Caught by Boston College. I don't believe it. Boston College has won it 47-45.
3, 2, 1, 0.
Look at the wave. Oh my hat, as they say.
Are we gliding?
Too low to rain. Too low to
Glide.
rain.
Pitch for glide.
Too low to rain. 100. 50. 40. 30. 20.
Brace.
10. Minimum.
Brace for impact.
Minimum.
All right, so unfortunately, the movie's over. Back to me. Now, if you want to count down, now you only got 9 pages of it, okay? So you get through 9, give or take, depends on how I can squeeze it on there, but around 9 pages. I always use that in PowerPoint. I see a professor, somebody give a talk in PowerPoint, like I'll be at a conference, like, oh, that looks like a big PowerPoint. Now, how many has he got? I'm looking at that scroll bar. Oh. First thing is you watch the guy come in and give a talk, he's got paper. And you go, that's a lot of paper. And then it gets worse. You know how it gets worse when he walks in with paper? Double-sided, flips it. I'm like, oh, I'm going to be here for a while. I might have to fake a heart attack. All right. Chapter 4. This should be boring as heck, actually. Hopefully it is. If you understood Chapter 3, we're just going to rehash it. At the end in Chapter 4, we will go into new stuff called radial motion, which will not be on the next exam. I keep saying that because I don't want you to think, oh, it's all Chapter 4. But the stuff we talked about in Chapter 3, we're going to do it now for just 2 and 3 dimensions. And because of our coordinate system, we're going to be able to, like, hopefully keep it nice and separate. We just got to make sure we get the right numbers in the right spots. So motion in 2 and 3 dimensions. It's ironic because I always say, oh, I don't stress 3 dimensions. Well, in Chapter 3, we started off stressing 3 dimensions. We worked in 2 also. We worked with vectors. And in this one, we're going to work with 3 dimensions today. And I don't know, depends on how we do it, maybe a little bit on Wednesday. But after that, we go to projectile motion, which is all 2D, and radial motion is all 2D. So after this, we pretty much will leave 3 dimensions alone as far as new material. So what did we talk about in Chapter 3? Well, we started off talking about position. We're going to be doing this now with in 3D. So position of an object in 3 dimensions. So we're going to need a position vector. When it came to 1D, we just called the position vector like X, X vector. That's usually where we started. You could have made it Y or Z, but you only need one of them. But we're going to need something a little bit different than that since we got all 3 dimensions working with us now. So the position vector for a point out in space is just going to be vector R. here we go. You're going to watch me try to draw something in 3D on a 2D page. So welcome to give it your best shot. I think you can guess the X and Y here. Now, some folks said in the other classes, oh, I reversed my axes. I have the Z going somewhere else. You know, and that's fine. You should always write your X, Y, Z axes on anything. For me, just getting a good habit for me, but let's face it, for your, I don't know, I guess you won't be writing anything in your careers, but you know, you should indicate it somehow. Type it in or write it on your PowerPoint, whatever you got, so that everybody knows what you're talking about. So, because some people have their axes reversed. All right, the X and Y axes, that's fine. I've got to draw a three-dimensional axis. I got to draw the third one, the Z. The Z is going to be coming, that's what it should be doing, coming out the page. Of course, I can't draw that unless I get some Lego blocks in here or something like that. So you get the picture, hopefully, literally. I'm going to draw my Z axis at somewhat looks like an odd angle, but really it's coming out at the page at you. And to indicate, this is a Cartesian coordinate system. I'll talk a little bit more about him in a second. All our axes are at right angles to each other. Indicated by this little, I should say red box, but I don't know how it's going to turn up when I scan it in. Hopefully I keep the color. But anyway, this box, partial box, means 90-degree angle. And we're going to have some kind of point floating out in space. And that's my position vector R going from the origin to wherever this point's at. And this point's going to be indicated by some specific and unique X, Y, Z coordinates. I'm my best to draw this, like, see a little how this is actually working here three-dimensionally. So this part right here is the X component for my R. This would be the Z component. And this guy here would be the Y component. So if we wanted to write our vector out, we would probably have some number right now. It'd be our X component, I hat, plus Y, J component, plus Z, K component. That's kind of boring if the object just sits there. You'd like for it to be moving, and you could just write it like that. But you know, the math guys and the physics guys do too, including your book. I like to write this a little bit differently to, like, you know, put a little emphasis that we are actually talking about an object which can be moving, but it's just mathematical, you know, window dressing here for an object that can be moving. Its position is written as, a little bit bigger here, R equals X, you know, X is a function of time. That's that funky X with parentheses behind, with T with it. So you just know, probably it's not going to be a number, it's going to be an equation. And it's just, you know, this would be chapter 3's beginning. We just have, you know, my position equals, you know, some function, some equation, and that'd be it. But now it can move X, Y, and Z. So I had to have a function for X, I had to have a function for Y, and I had to have a function for Z. All excited. And this would be my position vector. As a function of time. I probably should have written that as R with a T after him too. But I forgot to, so I'll just leave it like that.
Is time in parentheses, or is that a divided?
This is it's in parentheses. So here, I'm going to write that in here. Yeah, this is when I say X with that T, I always say X sub T. But it's not a subscript. This means X is a function of time. It's an equation. And this does not mean x times t. Okay. It's just a mathematical way of writing. Say, hey, you know what? I'm going to have an x component. It's probably going to be an equation. It's going to vary with time. Okay. Hopefully I'm not going to. I don't mean to smoke screen you guys with the mathematical stuff. Those math guys, man, they're crazy. Any math majors out here? Now you're not going to admit to it. It's good to have laws. I take a few too. I cut a few too many corners, I think, at times too. So if you can't understand what I'm writing, please heads up. But like I said, that's what the book's got. You open up the book. That's what you'll see. I recommend skimming the book. Sometimes I try to make that book really thick with a lot of superfluous stuff like I do when I talk or something like that. To make it look more important. Okay, we're going to leave that for just a second to give you a warning. And the warning comes from the fact that your X stuff stays with the I hat, the Y stuff stays with J hat, and the Z stuff stays with K hat. So you'll have an equation for X, perhaps, and it will the only thing it will give you is your I component, your X component. Same way you'll have another unique equation for Y, another unique equation for Z. They don't affect each other. The Z can be bouncing all over the place, and X could actually be a constant. It can be just plain 0. So it'd be a 2D problem or a 1D problem at that point. But yeah, so they don't affect each other. We have to keep that in mind.
Mother! I've turned the cooling unit back on! Mother!
Ship will automatically destruct in T-minus 5 minutes.
We use this Cartesian coordinate system. The Cartesian coordinate system, aka the XYZ system. Probably sure beats the Cartesian coordinate system all the time. So, comma. The axes are perpendicular to each other. So they're drawn such that each axis quantities, what I mean by that, I mean by position, velocity, or acceleration, are independent of the other two axes. Okay. The Cartesian, if you worked with some math before, I mean, you obviously work with math, but if you've done enough math, perhaps you're a high school teacher, perhaps you've had college classes already, and you'll find out there's other coordinate systems out there, and you already know that. Matter of fact, if you actually have opened up the book, they talk about the polar coordinate system. I played in chapter 2, and I just skipped it. I didn't even mention it all until right now, and I won't mention it other than right now. It's different coordinate systems. You use them based on what makes life easier for you mathematically. The polar coordinate system, very powerful, and the Cartesian coordinate system gets very clunky fast, especially if you got spherical symmetry, spherical things going in circles. But we don't do that. Even in radial stuff, we're going to be able to cut around that and still be able to use the Cartesian coordinate system for what we need it for. And we'll stick with this throughout the entire 174, 175 sequence. But you could actually use a different system if you had to. Our neat thing about the Cartesian coordinate system, it has lots and lots of problems eventually. Everything's perpendicular to each other such that the axes are independent of each other. So all the X stuff stays, in the X area, and it has no effect on the Y or the Z and vice versa. And that's also a little bit of the problem. That's not a problem. You have to worry about it anyway, but you got to make sure you keep the right quantities with the right axes. And that's the warning that comes in. It seems, of course, but no. What'll happen is I've already seen the problems coming up. I had that problem last week where I had a train accelerating. And the train accelerated for a while, and then it coasted for some more time. I threw a bunch of numbers at you in all these scenarios in this area, and then the train put on the brakes, and there were some more numbers there. And the question asked for was something about how far did the train travel while it was braking. I forgot what was the speed, what was the velocity of the train after 291 seconds. A really weird number. I think that was what the question asked for, and we struggled a lot. It was like, oh, what numbers go where? And that was a 1D case. Now you're going to have a three-dimensional case, perhaps, or at least a two-dimensional case. And you got to figure out, not only do you have to figure out what numbers are relevant, but where they go. Is this an X component? Is this a Y thing? Is this a Z? And so that's the warning. I like to think about these things as being in buckets. Consider the quantities I just spoke of as far as, position, velocity, and such, are in buckets. If you don't like the word bucket, box, area, whatever you want to call it, you got to keep them straight. I draw the stupid pictures and I hope it works. So here's my three separate buckets. You can only be just like anything else, you can put something in a bucket, but it's hard to put something in two buckets. So you got to make sure you put it in the right bucket. Put all your stuff away. This is only X stuff. This is only Y stuff. Only Z stuff. So over here, you're going to have your X naught, your X, your V naught X, your VX, and your AX, your components of your acceleration, components of your velocity for the X direction only, and your component of your position, the X component for that position. Over in the Y bucket, you're going to have the same things, except they're going to have Y's with them. You're going to have your Y components, and that's it. You don't, and then let's finish the statements here. The Z bucket, he's got his own stuff too. Things don't go well if you put your acceleration for your Z component for your acceleration in with the X stuff. It's not matching. It's like matching socks up. It just won't work out. Your motion in your Z cannot be affected by your motion in your Z. So your motion in your X can't be affected by your motion in your Z, or vice versa, or the Y's. So you got to be sure to keep these guys separate. Bucket quantity shown. Do not mix. And that's the problem we get. I fight like crazy, and sometimes I just throw a number down. I don't see it until it's too late. Numbers, I won't have, VX won't be 3 and VY won't be 3. They won't be the same. I'll try to make them all different or something like that, but just keep the heads up there. Make sure you keep them straight. Now these are, if you remember the equations of motion we've been working with last week, we haven't dealt with anything with Z, but we did go back and forth between X, and we ended with free fall, so we went to Y. We have all these basic generic terms for these quantities: a position, initial, final position, initial velocity, final velocity, and acceleration. Only one variable is missing from these buckets, and the reason it's missing, only one variable has a chance of being shared. By or between the buckets. Okay, and I said, okay, I know it has a chance. Doesn't mean it will, but it has a chance. What variable am I missing up there? It was in those equations of motion. The time. That's right, time. And the reason it can go back and forth if you're lucky, and there's no coincidence here, all these guys up here are vector quantities. Position, initial final, your velocity, initial final velocity components, and your acceleration. These are all vectors. They have to be broken into their components. We've done that since chapter 2. But time's a scalar. He's the only scalar quantity. In the equations of motion. And we're not going to deal with equations of motion today, but we're going to deal with them heavily after today. We've already dealt with them. It's going to go in two-dimensional, three-dimensional cases. Actually, in the equation of motion, we're only going to deal in two-dimensional cases. But yeah, we got to be careful. Time can go back and forth between a bucket. The time it takes you to go from X naught to X final, if the problem is so worded well enough, or if it's, you got to make sure it does apply, it's the same time it takes you to go from Y naught to Y final. Okay. And I'll just put it in red. Be careful not to mix other things. You still got to make sure the time is applicable. You can go back and forth, but definitely the other stuff will not mix. Okay. So if we deal with projectile motion, the acceleration of negative 9.8 meters per second squared in free fall. What coordinate system would that be on? What bucket would he be in? Most likely. Y. Okay, we generally make the Y vertical. Can't put AY equals this for AX. And that it happens. I hope it won't happen, but it will happen. It will happen. It's always happened. It's always doomed to repeat no matter how I draw buckets or boxes or being brought in Legos and that. Yeah, I'm hoping to get as many as I can. You'll see, you'll do a projectile motion problem, and then you'll be filling out the scorecards. Now you got to do 2 scorecards, one for the X's, one for the Y's. Here's AY equals negative 9.8. Well, what the heck? Let's make it equal AX. Please don't do that. It seems easy now, but it'll happen. I hope it doesn't, but it usually happens. So the acceleration for one side doesn't mean it's acceleration for all of them. So be careful about that. Okay, that's my warning. We're going to go back to positions vector now. I said we were doing how many pages? Like 9? I'm already 5. So back to the position vector. Well, dealing with position vector is nice, but we want to know how it's moving around. Where it's going is great, where it's going to wind up, but how fast is it going to get there? Of course, what's its acceleration? And the acceleration really comes big because we've been talking about G forces and such. It's getting us ready for the next chapter, chapter 5, which deals with forces, and that's when things, fall down or when things become lethal to you, and that deals with acceleration. So we're going to go for that velocity, but before we get velocity, we got to talk about the displacement vector, as we did in chapter 3 at the very beginning. In a 1D case, we just wrote delta x equals x final minus x initial, or x naught. We generally drop the f or the subscript. Anything without a subscript is generally a final, or at least not necessarily the end of time, but it's the end of our interest for a problem. But I'll write out here because it's been a little bit of time since we talked about it. And the deltas are used, I don't know, like I said, universally, but as far as physics 174 and 175, we never use deltas to mean anything other than a change of. It's a change from you subtract out your initial from your final. In 3D world, our position vector is no longer x, but now r. So this should not be too scary for you if you accept that. Delta r is going to be r final, your final position, minus your initial position. So be described by x naught, y naught, and z naught. And this is your final position. X, y, and z. And for that case, I'll just drop the little f. Okay, understand the picture here. Let's continue that chapter 3 analogy. Next up on the hit parade was to figure out what velocity was. So instantaneous velocity. We could talk about average velocity, but we talked about basically it wasn't the greatest thing to work with. You can get around it, you did. And so we're going to do that today. And for the best way to do it was to figure out a derivative. If you knew your position, an equation representing your position for all time, you just take the derivative with respect to time, and out will pop your velocity. Remember, R is going to be this. If you don't like to write the T, I understand it, but just remember, it's probably going to, it will be an equation. Probably at least one of them will be an equation. Otherwise, like I said, if there's no equation here, the object's just sitting there in space, and that's good to know, but it probably won't happen. Definitely won't be of any interest to us. So that's generically how we wrote it. And we're just going to take a derivative of that. Go generically, and I'll do an example of it. So equals dr dt. And that means I have to take a derivative of the x component, derivative of the y component, all these with respect to time. And finally, poor little z, always the last guy I mentioned, d0 dt k hat. I say you gotta keep everything straight now, so when you do your position, you only stick in here the equation for the x component for position. You take the derivative of that term. You don't put the whole equation in there. Now, I mean, if you did that, you think, well, my gosh, I'm going to do it for every one of these. Yeah, you'd have every term 3 times. So you just put the x component, his position, take the derivative of him, move on, do the take the derivative of the y component's equation, or formula, or function, whatever you like to call it, and move on for z. And when you get done, either, well, you probably have an equation. I should put this as equation as a function of time for the x component for your velocity. You have an equation for the y component and an equation for the z component. I make no bones about this. So heads up, this is a calculus-based class. Oakland's expecting me to deliver a calculus-based class to you guys. We've now gone back to talk about derivatives twice. On exam 1, you will have derivatives, okay? Not many. Just for all I can say, and it's, I don't mean to scare you about it, just hopefully you think, well, this is easy. I'm hoping you do. If not, if it's been a while for you, you're still confused by this, please see me. They will be on exam 1. You won't have to get it to pass the class or even to get a high grade, but just it means you got to do well in the other problems too. So, or who knows, this could be a long problem, and that would actually have a big impact on you. So yeah, just make sure you get it down pat before that exam comes around. Calculus will be on your derivatives. And this is about the only time we talk about derivatives until we hit impulse. I forgot where we're at, but it's going to be a while, but you can always refer. Everything builds upon this. We can always refer back to this. Is the only place we'll see new derivatives for quite a while. Likewise, the instantaneous acceleration. That's just going to equal a, and that's the derivative of your velocity function over time. So you have this function of for your x component for your velocity. you take a derivative of him. And I'll give you your x component for your acceleration. To get your y component for your acceleration, you move to the function you have for the velocity's y component. Derivative of that guy. And finally, you do it for the z component. When you do that, you'll be left with ax is a function of t, plus ay is a function of t, perhaps, plus a sub z t k hat. Be careful, like I said, make sure when you do these problems, make sure you're solving for what you need to solve for. Definitely a good time to show your work. I mean, that's happened to some of you guys when your homework, or I forgot the homework or quiz, whatever we had for it. I think for one of them, I gave you a position. And actually, for something about acceleration, you had to take two derivatives and you got your acceleration. And one of those guys actually gave you the velocity. I want to see if you're thinking about it. And actually, for the acceleration, you only take, if you're at the velocity, if you already got this equation and you get to get acceleration, just take one derivative of this guy and you're home free. Some people went twice. So be careful, you know what you're looking at there. Time for me to do an example. Example, poorly written example. Maybe if I stand up a little bit better. Suppose you know the position of an object for all time t to be given by, when you're going to use a derivative, you're going to be presented with some kind of function equation, and that equation has to be given to you. There's no way to get it. I mean, there are ways to get it, but not in this class. Involves integration, stuff like that, or computers to record the data, like I've mentioned several times before. So this would have to be given to you. Some more here. This says no. If this has any natural implication, I've gotten lucky because I just pulled an equation out of the air and started making it. So here we go. So here's this. This would be it for the chapter 3 beginning, but this is actually just one of our components now. This would be our function of x as a function of time t. As time goes by, our coefficient, our x component will change. Plus negative 8t squared plus 3t. This is my function of my y component as a function of time. And finally, just making this up, like I said. So I got, I think I used this one last year. So I didn't use the same time. Okay, so that's my z component for my position. And then so this would be the problem presented to you. And I say find your position at t equals 2 seconds. Okay, so I'm looking for my position. This is my position equation. So that's an easy one right here. I just plug in 2 for t. And I guess I forgot. I didn't give any units up there. And if this were a problem, I would try to fight my best. I'd say something like, the units are such that if time is given in seconds, R will be in meters. And that gets me off the hook from having to write all my units in here for one of those terms. So, I mean, they would all be different. Well, okay, any power of t would have a unique, unit for its coefficient. This guy here would have to be meters per second cubed, and this one here would only be meters. But that gets me off the hook. Otherwise, it'd be really entangled. And of course, if you're actually writing articles or something like that in life, not for me, but in future professional career, you would have to put all the units there, but don't want somebody guessing the wrong units. Look what happened to NASA. So you just stick in your time. Oops. 2, 3 power plus 8 times 2 squared minus 10. So let's just go up here. Just plug in t equals 2. Whatever reason, I want brackets there, and I want just parentheses over here. Okay, let's just plug in all your what t is. And I heavily suggest on an exam, if this is a long problem, to actually show me this. You don't have to show all the math. Just show me you're sticking in. Look, Professor Brown, I'm sticking in my time here. I'm the first guy to admit I make mistakes in this too. I try to do it in my head, or I punch it wrong with the calculator. You don't want to go from here to here. Like, what did you do there? Did you take another derivative? Why didn't you get the right answer? So definitely got to show your work. I take a little bit off if it's right. There's no work there. Now on the exams, I'm a little bit more lenient, but it's if it's wrong, it's everything goes. I mean, you got. If I don't know what you're doing, if it's the wrong answer, it's really, really bad. Right? So, but that's the answer here. This is the answer for this guy. Hopefully, no one seemed to raise any objections in the other 2 classes. This, of course, is that value. Hopefully, that goes there. And of course, this is my z component. It's right there. Anybody want to guess what we're going to do now? How about Tyler? What are we going to do, buddy? What would you do if this was your class? What would you do next? You bet. I want to get the velocity. I want to know the velocity. I want to know everything about this part. I don't care. This is neat. I know where he's at. But how fast is he moving? Should I get out of his way? Is he moving so fast he's going to hurt me? So let's find the velocity at equals 2 seconds. Careful about that too. The book's got some too. It's like, hey, here's what's the position at t equals 1 second. And then you go to the next part and it's find the velocity at t equals 5 seconds. So, and I think I switched around like that too to make sure you guys are up there on that one. But usually, especially on exams, I wouldn't do anything like that. But just make sure you're practicing or something like that. Make sure you're sticking the right time. So find the velocity at t equals 2 seconds. This is not my velocity equation. Some people thought that in a homework quiz, whatever it was. This just tells me my position to get my velocity. I mean, right now I don't have an equation for it, but I know how to get it. I just take the derivative of this position equation. It's going to be dx sub t over dt I hat plus dy as a function of time over dt, and dz is a function of time over dt. Yeah. Once again, these are probably, and they are, every one of these terms is an equation. If it's not an equation, that's okay. You're just going to take the derivative of a constant. What's the derivative of a constant? Well, 0. I mean, that's the easy case you're looking for. No, not necessarily given to you though. Or not going to happen. So let's see. Let's write it all out. V equals. I had to take the derivative of, like I said, just the x. We don't want to mix these buckets. So just this piece right here. Okay. Then just move on. I want the derivative of the y position. Just this guy right here. And finally, one more time, I work with just the z's. Okay. Now you're at the point where you got to take actually the derivatives. Definitely also tell me you're actually dealing with derivatives, okay? That's some of your homework and stuff like that. I beat you down hard on that. If somebody just gave me the answer, I know they're pretty easy derivatives, and I did the problem, so I know, yeah, that's probably it. But for heaven's sakes, if you make a mistake and you don't tell me you're taking a derivative, you make a mistake, and all I'm looking at wrong answers with no idea how you got there. It's a buzzsaw for you. I mean, there's very low partial credit. They're next to nothing other than the fact you showed up for that exam or whatever. So thank you very much. It's just, don't do that, please. Oh, you do something, say something simple like, I'm going to take the derivative now. Or some people like to write this as x prime, x double prime for the acceleration. And that's fine. I know you're taking a derivative now. Rules of derivatives are in place. If you make a mistake after that, I know, well, it came with the derivatives. And yeah, but you tell me what you're doing, more than likely, you're just going to be just fine completely. But here we go. All right, I'm taking the derivative. You went ahead and show, I'm just showing, I wouldn't show this next step actually. I would skip to the next one once I show this guy, but for those who haven't had derivatives, let's do it. So you take the power down. I got 25 times 3, t squared, plus 8 times 2, t to the 1 power, minus 0. I definitely won't write that 0 in there, but those folks who haven't had it in a while or haven't had it at all. Move on to this guy. Negative 8 times 2, t to the first. I see it, t to the first. And then plus 3 times 1, t to the 0. J hat. I'm getting a little closer, so let's just keep it far apart. Sorry about that. 10, move down to the next line. 10 times 3, t squared minus 5 times 1, t to the 0, k hat. Okay. And unless the numbers are just so crazy, I wanted to write them down to make sure I didn't mess anything up. Like I said, I would have gone from, if anything, this step, I'm taking a derivative, to the next step, skipping this guy, just doing the math out in my head as I went along. Or at least this step. Let's see. So we have 75 t squared minus 16t. Who cares about the 0? Minus 16t plus 3 j hat plus 30t squared minus 5 k hat. And when I look to my right, I see if I got my same, if I didn't make a mistake myself, and hopefully I didn't. Just to keep you guys going. Now this is your x component for your velocity. This will be your y component. Because sometimes these problems will ask you, they'll do something, they'll say, you know, what's the z component of your velocity? Oh, don't solve the whole thing. Just, or if you do, make sure you zero in on this guy. Find your z component. This equation here tells me the velocity for all time. Really, really powerful. But the question does ask for velocity at 2 seconds. So at 2 seconds, I gotta stick in my 2. Why bracket there? Okay. Like I said, once you got this, show me what you're doing. You don't have to go through and write all the little steps out. If you want to, actually, that's a good idea. I mean, you can help yourself in case you think you're going to get an error. But I would just skip, that'd be the first guy to admit, I'd just skip to this step here. Crank these out on the calculator, and away I go. That's your answer. So no one's saying anything of 8 o'clock or 9:30, so I'm guessing, hopefully, that's good. One more thing left, that's find acceleration. Keep that there. Page 9, this is it. Then you guys got to do stuff in class, but at least get away from me yakking. Find the acceleration at t equals 2 seconds. Acceleration equals the derivative of your velocity equation with respect to time. So once again, we keep all those buckets separated. That's going to be dv of x at t equals, oops, not t, same thing, dv this time t, or dt I hat plus your derivative of your y component velocity, or dt? Yes.
For the I hat, shouldn't be 75 2 squared plus 60.
Which one right here? Alex, what, 75 t squared?
Yeah, shouldn't be a plus right there.
Oh, well, let's see. Oh, you're right. Thank you, Alex. Thank you very much. Yeah, I kept it. I didn't. Yeah, the answer is 332 though. 332. Calculator now. Oh, why wrote a negative there? Now I gotta do it. 4.
Yeah, you got the.
I got the right answer, right?
Yeah.
Well, that's the important thing. No, that's not the important thing. Okay, watch out here. Thanks, Alex. The up here is right. And then for whatever reason, I just start forgetting that negative sign or the positive sign. So I'm going to see where the red goes. Everybody got that? I think these are my only two bad guys, right? All right. If I copy it now in black and white, you'll never know I made a mistake. Everybody out there, hopefully people are still out there. Well, they're not listening. 5 minutes ago, they won't even know it, so they won't see the mistake. But okay, those two terms right there should both be positives. Because I took that up here. It's Monday. I just felt a little down, I guess. I wanted to make them negative. That is the right answer. Thanks. Dang, that's sad. Okay, back to the riveting story, the conclusion here. And you take your derivative of your z component. I mean, come on, this is great stuff. With respect to time, and that's going to give you my accelerations x component, or sorry, z component. So there we go. So let's see. Better write that all the way in here. So I go up here and I find Vx. There he is. Now with a little red tag there to give me the right sign. Okay. Keep reading over here. I take the derivative of the next function for the y. And finally, one more time, the derivative of the z. Component for velocity. Get the z component of acceleration. So see if I can do this now. So 75 times 2 is 150 times t. This time I'll leave off the intermediate steps where t is 0 or something like that. 16t, the derivative of that is just 16 I hat. Take the derivative of this term for the y. With respect to time, you're only going to be left with, since the derivative of a constant is 0, you're left with negative 16 j hat. And finally, for the z component, you're left with just 60t k hat. So that's your generic equation for your acceleration for all time. Note, ax and ay are not constant with time. In other words, they vary. So you plug in as t is 1 second, you're going to get one value for ax and ay. You plug in 5 seconds, 5 years, what have you, and they'll also change. But ay is constant. If you're given enough information, you actually could use the equation of motion on ay, and you'd be able to get the same information as you would taking the derivatives, provided you had enough information. You'd have to know your initial velocity and along the y-axis, final velocity along the y-axis, whatever it took to solve that equation. That was one of those equations of motion, like we did on Wednesday and Friday of last week. So these guys here can't use equation of motion. And you couldn't for this problem either. I mean, it's either going to be one or the other. There's not enough information given for this problem. In order to use equation of motion, you got to know several things. You got to know, like I said, initial positions, initial velocities, final velocities, all that stuff in order to fill out that scorecard. Here, though, you got to do is take derivatives. I guess the answer was, or the question was, what's the acceleration at t equals 2 seconds? And that's going to be 150 times 2 plus 16 I hat minus 16 times j hat plus 60 times 2 k hat. So my acceleration at t equals 2 seconds equals 300 plus 16, 316 I hat minus 16 j hat plus 120 k hat. Hopefully. Gotta check my answer now. Pages in my notes are way off now. There we go. I don't like that. There we go. It's a little bit better. Okay, that's the answer. All right. For you guys at home, get on that, scroll down on Canvas and get that handout I gave, or there's only 2 things in the Canvas account there should be. One was the movie we just saw at the beginning, and the other was a handout. The handout, I tried to do something better. That's why I ran out of time last night. I thought, there's a better way of doing these handouts, because it's getting so long, the Canvas things are to scroll down and find the right thing. So I took all the problems I thought we were going to work on for this chapter leading up to exam 1, and I stuck them into one gigantic PDF file. So we're only going to we'll do the problems as they're relevant in the class. Right now, you probably could do them all, but we're only going to be dealing with the first part right now. And when I say the first part, yes. Yeah. Yeah. You see, when I plugged in a T, this AX, oh, sorry, my bad. Thanks, Alex. I'm thinking I need to get out of here. That's what AX and AZ. Now you happy? You happy now? Oh, I don't know why you'd be confused, because I wrote 2 things twice. Yeah, that's very good. Be confused. Very good. Thank you very much. How about you come to class all the time? All my classes, make sure you catch me on those little mistakes all the time. It's like I should hand out prizes or something like that. Actually, I can't give out prizes, but I'm saying I can't touch anything now. So a virtual high five. There we go. So we're looking at this guy right here. Oh, I don't want to show you that because the other class has it. So we're looking at the this packet, but we're only going to be looking at the first one. Unfortunately, it's 8 problems. But don't panic. It's just position. It's just what we just did right now. So I'm going to hand it out to the class. You guys online, download it, open it up. Hopefully tell me if you can't get it online. And if you're looking at the answers, we've already found this mistake. This is I at least found before they found it on me. This right here was, and you guys should be corrected online. I upload the new version. You guys here in this class got the handout before I saw it this morning. So the G is off. Just a little bit on the Y component, but hey, if you're wrong, you're wrong, right? People die. So, yeah, it should be that G is, the Y component is not -48, it's -24. So ironic. It looks like a bad cut and paste job. It looks like I did H first, but I did it last night. I don't think I did it in reverse order. Okay. I'll be having office hours today, so if you want to drop in real or virtually, remember the password is NeoWise. I'm almost positive it's NeoWise. I cut and pasted the screen, and before I changed the password. It's the password you use every day to get in this class.